and thank you for tuning in. Welcome to a new episode of the Passion for Technology podcast by EBV Electronic.
Welcome to the Passion for Technology podcast. Today we continue to explore digital motor control. The term often brings to mind images of advanced digital motors in appliances like vacuum cleaners, just like in old TV commercials. But what essential electronics are needed to implement digital motor control? And what should you be mindful of during the design process? Let's dive into these topics with today's guest, Canberk Sezer, who is a field application engineer for digital motor control software at EBV Electronic. Hi, Canberk.
Hi, Mustafa.
Canberk, what are the essential components and parts required for implementing digital motor control?
Actually, when answering such a question, we need to focus on the word digital, because the innovative aspect of motor control lies in its digital implementation. The digital control method begins with the addition of a microcontroller to the system, and this allows the realization of desired algorithms and calculations on software. Of course, the microcontroller needs to collect data from its surrounding and process this data based on it. For feedback, various types of sensors can be added to the system. Determine the position of the motor, encoders or resolvers can be used through digitization. Observer algorithms can predict the motor's position. In high-power systems where values that can create input to these predictions can be acquired from auxiliary components such as current sensors and voltage sensors. Actually, up to now, the digital side I have mentioned involved components focused on data collection and decision making. To complete these systems, we need inverters that can implement these decisions at the desired power levels, and the driving circuits for these inverters. These circuits include power elements, such as gate drivers, MOSFETs, or IGBTs. Additionally, wide bandgap products, whose popularity is increasing nowadays, also fall into this category.
So, Canberk, how does the choice of motor type, such as brushless DC versus permanent magnet synchronous motors, influence motor control? What implications does each type have?
I would like to answer these questions by directly comparing the two motor types. In case of BLDC motors, their control is comparatively simpler than PMSMs. Typically, BLDC motors operate with trapezoidal control or six-step commutation, which is less complex than the field-oriented control utilized in PMSM, field-oriented called to FOC. In terms of sensor requirements, BLDC motors often need to position sensors, like Hall effect sensors for commutation. While sensorless control is possible, but its accuracy may be limited at lower speeds. Common applications for BLDC motors include scenarios where simple control, good efficiency, and cost effectiveness are important, such as in fans, drones, and specific automotive systems. On the other hand, PMSMs offer superior efficiency and performance, particularly at higher speeds compared to BLDC motors. However, controlling PMSMs involves more complex algorithms, typically FOC. Accurate control of PMSMs typically requires position and speed feedback sensors like encoders or resolvers, and sensorless control methods are more complex. PMSMs are commonly used in applications where precise control, high efficiency, and dynamic performance are imperative, including industrial automation, electric vehicles, and robotics. Ultimately, the choice between BLDC and PMSMs depends on factors such as the application's performance requirements, cost perspective, the desired level of control complexity. In a broader context, motor control techniques and algorithms are tailor-made to suit the specific characteristics and demands of the chosen motor types. Thus, a deep understanding of the motor types, behavior, and control methods is critical for designing effective and efficient control systems.
And BLDC being brushless DC and PMSM being permanent magnetic synchronous motors, right?
Yes.
So, Canberk, what's the recommended starting point in the development process for digital motor control?
Firstly, system approach is needed to develop motor control. To talk about the steps of this system approach, to begin with, it is crucial to define your project requirements with all details. This includes outlining performance specifications, control accuracy, speed range, torque needs, etc. Once these requirements are crystal clear, the next logic step is motor selection. Here you will choose the motor type, like as BLDC PMSMs, based on your outlined needs, and calculate efficiency, power density, and control complexity. After determining the motor, the focus shifts to sensor selection. Decide on the type of sensors required for feedback, such as encoders or Hall effect sensors. This choice significantly influences control accuracy and complexity. Following this, you will move on to control algorithm selection, tailoring it to your motor and application. For instance, trapezoidal control suits BLDC motors, while FOC is suitable for PMSMs. With the base choice in place, the development process transitions to hardware design. This includes developing the motor drive circuitry, gate drivers, power stage, and implementing current and voltage sensing, along with protective mechanism. Consideration like isolation, noise immunity, and thermal management critical at this stage. At the parallelly, you will need to select a microcontroller for digital control. Choose a microcontroller capable of handling the chosen control algorithms and processing the necessary feedback signals. After completing the hardware design, attention turns to software development. This phase involves creating the control software, implementing control loops, sensor interface, modulation techniques, and integrating protection features. As the software takes shapes, it's time to transition to a critical stage of testing and calibration. Starting with simple open-loop tests to verify hardware functionality, you will progressively advance the closed-loop tests, incorporating sensor feedback. Calibration of control parameters becomes important during this phase, ensuring the achievement of desired performance metrics. In summary, this step-by-step roadmap provides a holistic view of the development process, ensuring a methodical and interconnected approach to motor control development.
So once you've decided on all those various components, right, and you already mentioned the importance of testing and calibration, stepping back a little, what considerations are crucial to ensure the seamless integration of all those components in a digital motor control system?
While the answer to this question is quite big, the first step we mentioned for the starting point becomes the most crucial here. The adventure begins with a great analysis of all project requirements and planning what needs to be done. Technical calculations underlying these, of course, follow suit. When practical experience from both theoretical calculations and laboratory tests is added, the resulting product can function as desired. The field experience in this context is a critical factor. As everyone knows, technology is developing rapidly and success is achievable when we can keep up with it. This evolving technology needs an eager observation to determine the compatibility of products we use. Indeed, at this point, we as EBV filter all innovations, format them, and convey them to our partners in the projects we collaborate on. Similarly, based on this information, we provide support for component selection and excellent operation of the chosen components. Because, as I mentioned earlier, field experience makes significant differences at this point.
With energy efficiency being a critical aspect, yet another critical factor and critical aspect, what design factors should be considered to achieve a higher energy efficiency in motor drives?
When it comes to efficiency, we can generalize by emphasizing the importance of minimizing power losses. These losses can occur either on motor itself or on the motor drive. For the motor, the focus should be on minimizing copper and iron losses. There are more topics for the motor drive. First, we can discuss switching losses. To reduce these losses, the evolving technology of wide bandgap products can be preferred. Of course, for efficient use of these switches, control algorithms such as FOC should be sophisticated. Additionally, optimizing motor control parameters to align with the motor's operating conditions will contribute to increased efficiency. Beyond these generalized topics, look at the trends in the market. Integrated motor drives are now being favored for servo motor designs. The reason for this in terms of efficiency is that servo motors can draw high instant power by using silicon carbide drive design that can be both compact and efficient. Cooling may not be necessary or can be achieved from the motor body. Another example is in high power applications, where regenerative braking in high power motor control applications transfer power back to the grid, reclaiming unused power. Naturally, digital control methods underlie all of these topics.
Canberk, can you share common mistakes encountered during the development process of motor control systems, and what are your thoughts about them?
Sure. Actually, the most common mistake I encounter is underestimating the complexity of projects and attempting to create their own systems by making modifications on readily available examples. Thinking the project is easy. Trying to achieve results by modifying an example projects published by chip suppliers, for example, extends the project timelines. In some cases, it can even lead to the project not being completed. The mistakes here include not defining project requirements well, lacking a proper plan, being unable to select components suitable for the projects due to relying on a single supplier's example, and attempting to use developed software without a perfect understanding of the total, making only few changes. Despite appearing minor, these mistakes can have significant negative impacts on projects.
How does EBV Electronics support developers in designing motor control systems?
EBV Electronics extends support to developers in designing motor control systems by offering a spectrum of resources and service tailored to their needs. To begin with, EBV's teams include technical experts who have deep knowledge of motor control technologies and applications, like as me. We can offer guidance, recommendations, and insights into the latest trends and best practices. Additionally, EBV provides a diverse range of semiconductor components, microcontrollers, sensors, power modules, and other essential elements for motor control systems. We can assist developers in selecting the correct components that align with their requirements. Moreover, EBV frequently organizes workshops, webinars, and training sessions focused on motor control and related technologies. And these sessions enable developers to keep their knowledge updated and learn how to implement effective motor control solutions. Furthermore, EBV's technical team can assist in designing both the hardware and software aspect of motor control systems. We can support schematic reviews, component selection, and troubleshooting. For specific projects, we can assist with customization and adaptation of components and solutions to meet unique requirements. Our collaboration with various semiconductor manufacturers and technology partners expands developers' access to a broader ecosystem of solutions and expertise. After the design phase, EBV provides post-sales technical support to address any issues or questions during the deployment and operation of motor control systems. In summary, we have a structure that starts to provide support at the idea stage of a motor control project and continues this until the life cycle of the product is completed.
That sounds very interesting. That holistic approach is very attractive, I imagine. What tools do semiconductor manufacturers provide to expedite the development process for motor control systems?
There are many tools developed by semiconductor manufacturers in this regard. To explain this under general headings, to begin, manufacturers supply the critical one, evaluation kits and development boards as pre-configured platforms featuring essential components like microcontrollers, sensors, and power states. This supports developers in rapid prototyping and testing of motor control algorithms. Simultaneously, software development kits, called SDKs, offer comprehensive support with software libraries, drivers, and example codes tailored for motor control applications. These SDKs serve as a starting point for developers, easing the starting of coding and implementation of control algorithms. In addition to SDKs, semiconductor manufacturers provide dedicated motor control development software tools. These assist developers in designing, simulating, and fine-tuning motor control algorithms. Particularly, these tools often include graphical interfaces, simplifying the configuration of control parameters, transitioning to specific tools and resources offered by manufacturers like NXP, Infineon, Renesas, and STMicroelectronics. Each brings unique contributions to support motor control system developments. Beyond the motor control development toolbox, NXP provides support for model-based system design, integrating MATLAB packages for developing model-based motor control systems. And the other one, the Infineon, offers the iMotion product family and environment, a flexible development platform specifically designed for motor control. The other one, Renesas, offers the Motor Workbench, a desktop program that offers a suite of tools, libraries, and documentation of streamlined motor control development. Lastly, STMicroelectronics offers the STM32 Motor Control SDK, providing a comprehensive software development kit for STM32 microcontrollers.
I think the range of software that you just mentioned in terms of tooling that's available, that goes to show that there is no digitalization without software, and that obviously also applies to drive control. Are there any other tools that developers can rely on and build on?
In the area of motor control, digitalization is integral to software, and developers have a lot of tools at this point. Model-based design tools, such as MATLAB Simulink, with features like Simulink Coder and Simulink Realtime, enable the design, simulation, and testing of control algorithms through graphical modeling interface. And the other one, manufacturers provide, as I said, motor control software development kits, SDKs, equipped with pre-built libraries, drivers, and example projects. These SDKs support developers to quickly implement motor control algorithms tailored for specific microcontroller platforms. Furthermore, various software libraries offer pre-built control algorithms like FOC and vector control, seamlessly integrable into applications, and simulation and emulation tools play a crucial role, allowing developers to simulate drive control algorithms before deployment on hardware, or emulation tools offer hardware-like execution on a PC, simplifying all testing and debugging.
While we're talking about software, Canberk, what about security? How do I ensure security when it comes to motor control for my drive?
When integrating security into your drive, you need to pay attention to some critical points. Ensuring a secure boot process is the initial step, allowing only trusted software execution during startup to prevent unauthorized code execution. This established the foundation for a robust security framework. Additionally, prioritize secure communication using encryption protocols like TLS, SSL. This safeguards data communication between the different components of the drive control systems, protecting against eavesdropping and tampering. And other critical point is that developing secure over-the-air called the OTA update mechanism. This mechanism facilitates timely software and firmware updates while ensuring authenticity and integrity, addressing emerging security threats. I would also like to add this advice. Consider the use of hardware security modules, HSMs, if applicable, to securely manage cryptographic keys and sensitive data, adding an extra layer of protection to the drive control system. Lastly, collaborate with cybersecurity experts such as EBV. This collaboration ensures ongoing insights and support, maintaining security resilience against evolving cybersecurity challenges from inception to completion.
Why is developing a custom digital drive solution beneficial, let's say, opposed to using pre-existing solutions from motor manufacturers?
There are actually several reasons for this. Firstly, customization takes the lead. Developing your own solution allows you to tailor it precisely to your application's requirements. You have control over algorithms, features, and performance, which might not be possible with off-the-shelf solutions. Through customization, we gain the chance to adjust performance optimization on the product. This enables us to find the optimal point for your design to operate under its specific conditions, your conditions at the area. Additionally, since you shape the design, you can add specific features, set it apart from other products in the market, or imagine a new feature that shapes the market. With the features mentioned so far, you can position your product differently in the market. As a progress of these efforts, you also secure your differences under the intellectual property, allowing you to maintain your position in the market. Besides, in terms of project sustainability, there are advantages. For example, if you have your design at the market, for the second one, considering your design as a starting point, you can quickly introduce different products to the field with just a little modifications. Lastly, cost efficiency, a crucial aspect for companies, is significant for creating your design. In the long run, having your own design will positively impact company profitability and increase financial gains compared to ready-made designs.
Do you foresee a future dominated by digitally controlled drives? How do you expect the market to evolve in this area?
I hope so. The growth of the sector in which I specialize is invaluable to me. Certainly, expectations are currently in line with hope. The trend toward digitization and Industry 4.0 is expected to continue. More applications will shift from analog to digital control to benefit from higher precision, flexibility, and integration with data analytics. Additionally, as energy efficiency becomes increasingly crucial today, digital control continues to take the forefront in enhancing efficiency in motor control in every possible area. In parallel, the evolving fields of AI and machine learning, when integrated with motor control, help companies increase predictability and reduce expenses arising from errors. Therefore, it can be observed that digital control will be preferred for all types of motors in the future. At EBV Electronic, we are strongly continuing our efforts in this regard and are ready for the future.
Canberk, you're obviously very passionate about digital motor control and all the related aspects. What I'd like to know is, how did you develop your individual passion for technology? What do the origins look like of your passion for technology?
I can provide a somewhat romantic answer to this question because this passion coming from my childhood. I grew up in a village and we had a large garage. Since my father was a machine technician, every kind of tool imaginable was available in that garage. Spending the majority of my days there as a child, I constantly tried to understand how different tools worked. Growing up with this excitement and curiosity, when I became an electrical engineer, I moved to sites where I could actually develop these machines. I still enjoy following evolving technologies with the same excitement and researching how these innovations can be applied in various fields. Exploring all the technical details feels like solving a puzzle to me.
That's beautiful. There is nothing wrong with romantic origin stories. So thank you for sharing that with us. And also thank you, Canberk, for all the other insights that you've shared with us today. Dear listeners, as always, you can find more info in our show notes. Please feel free to subscribe to our podcast, Passion for Technology, on either Spotify, Apple Podcasts, or any of the other popular podcasting platforms. Canberk, thank you for joining us today.
Thank you, too.